Hey everyone, in this video we will be talking about L'Hopital's rule. So before we can talk about L'Hopital's rule, we have to talk about indeterminate forms because these are the limits that we will be using L'Hopital's rule for. So what is an indeterminate form? So these are things like 0 over 0, one of the infinities over another infinity, and we'll even see like a 0 times an infinity. So you may say like, okay, anything, 0 over anything is 0, or somehow we should be able to divide infinities, anything times 0, 0. But we'll see examples where these are not necessarily the case. So where do these show up? All right, so let's look at 3 different examples here. So the first one is something we've seen before, right? So, okay, let's see, we plug in 4, we get square root of 1, aka 1 minus 1 over x minus 4, but 4 minus 4, so it's 0 for both top and bottom, right? But we know the trick here is we can multiply by the conjugate, we'll get some factor we can cancel, and then we get out just a finite number. We're not going to go ahead through this because this is a L'Hopital's rule video, but this one is doable. The next one we've also seen, right? So limits at infinity. Well, both of these are going to infinity, right? As x increases, then the functions are going to increase. But we can't just divide infinities and say this goes to 1 or anything. We see that the higher degree is in the numerator, and so the numerator is growing faster than the denominator, and so this limit actually is positive infinity. And then on the third one here, we can say something similar. It's not exactly a compare the degrees, right? Because e to the x is not a polynomial. However, e to the x grows much faster than x does. And so this is again infinity over infinity, but the infinity in the bottom is way bigger or growing way faster. And so this one is actually going to 0. So now we're going to see how L'Hopital's rule can either make some of these a little bit quicker or can deal with ones that these methods like multiplying by the conjugate or examining how fast the numerator or denominator grows isn't going to work. So let's see what L'Hopital's rule says. So here's the statement of L'Hopital's rule, and this is really nice, right? So we start with some quotient, we take the limit of it, and then we get the limit of the derivatives. Now, this isn't always true, and so it's important to know when we can actually apply this. So first, I mentioned derivatives here. So f and g better be differentiable. Otherwise, how are we going to take the derivatives? So that's the first requirement. And then second, and really we'll break this into a couple cases, this only applies for these indeterminate forms, but specifically we want 2. So one of these cases must be fulfilled in order to apply this. So that's why I have A and B here. So either we're in the 0 over 0 form, so both the numerator and denominator go to 0 as x goes to A, or they both go to one of the infinities. And you can have different ones. So like infinity over minus infinity is perfectly fine. Okay, so L'Hopital's rule only applies if these things are satisfied. So let's consider this example. So you could take a graph or something like this and see what's going on. Essentially we're dividing by a really small number and maybe getting really big, but at the same time we're oscillating, and so we don't really know what happens. And this is a 0 over 0 form, right? Sine of 0 is 0, x at 0 is 0. So we fit 2a, and we also fit 1, right? Sine and x both have very simple derivatives, so L'Hopital's rule applies. And so, I'll often put like a L apostrophe H here just to say what I'm using. But we can then simplify this to cosine x over, well, now it's just 1 downstairs. And so this we can actually evaluate, right? So as x goes to 0, cosine of x is going to go to 1. We divide by 1. We get 1. Okay, so this is a nice, easy example using L'Hopital's rule. So now let's make it ever so slightly different. So again, this is a 0 over 0, but now I have an x squared instead of x in the bottom. So after my first turn here, I'm going to use L'Hopital's rule. I get the limit of cosine again, but now over 2x. And so here you're like, okay, well, this isn't immediately obvious, right? So I use L'Hopital's rule again because I don't have a nice constant down here, and I can get rid of that and make it a 2. But hold on just a second. Remember, we have to satisfy both of the hypotheses. Is this an indeterminate form? So the bottom is definitely 0, but the top here is 1. So we can't use L'Hopital's rule again, but we also don't need to. This limit does not exist. Okay? So be careful of that. All right, and so for your first exercise, I want you to take a look at the limit as x approaches 0 of 1 minus cosine x over sine of 2x. So earlier I mentioned this third indeterminate form of 0 times plus or minus infinity. So we wonder, why is this not taken care of by L'Hopital's rule? Well, let's see how we can actually use it even though it doesn't seem like it fits, right? Because this isn't a quotient. So let's take a look at the limit as x approaches infinity of x times sine of 1 over x. Okay, so x is clearly going to infinity, and sine of 1 over x, well, as x gets really big, it's really like basically sine of 0, right? And that's why this is infinity times 0. Okay, but it's not a fraction. But remember, 1 over something going to infinity is going to go to 0, right? So if we take this x and instead divide by 1 over x, maybe we're in business. So let's look at this instead, because x is equal to 1 over x. Sounds stupid, but again, this rewriting things, you've seen it before in terms of like factor and cancel or multiplying by the conjugate, that helps us figure out a solution. So now we have sine of 1 over x up top, and 1 over x is our denominator. Well, now this is going to 0, and 1 over x is going to 0. Now I have a 0 over 0, and now I can use L'Hopital's rule. Okay, so what are my derivatives? Well, I now get cosine of 1 over x, but I have to do the chain rule, so times negative 1 over x squared, all over negative 1 over x squared. Well, these guys cancel, and so it's really just cosine of 1 over x, but x is going to infinity, so this is cosine of 0, aka 1. All right, and for your second exercise, I want you to look at the limit as x approaches 0 from the right of x times the natural log of x. And it's just 0 from the right because ln is not defined for x less than or equal to 0. So we kind of have to do this, but L'Hopital's rule and stuff works out just the same for one-sided limits. All right, thank you for watching.